So I think we can start. So, hello everybody. This is Luboš Pirkl and Radek Máca from CFD Support. Welcome to the webinar on Turbomachinery CFD, which is a smart, easy and affordable CFD software for rotating machinery. I hope everything works well, all the techniques works well. So, well, anyway, in case of any technical problems, feel free to contact us in the future, and we will gladly answer all your reminders and questions. The topic from today's webinar is centrifugal compressor. So today we will deal with centrifugal compressor. I think we can go. So let's start with who we are. So please let me introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support, and today I'm sitting here with Radek Máca. Hello, Radek.
Hello, Luboš. Hello, everybody.
So how are you today?
Yeah, I'm fine, thanks. And first, let me know that Luboš is a great guy, great boss, and he is our visionary, and it is always a pleasure to cooperate with them, to work with them. So I just want to say this before you start.
Okay, thank you, Radek. Yeah, you made a good impression on me and on our participants. So thank you. So I will only note Radek is our head engineer and senior developer here at CFD Support, and he will take care of the technical part of today's presentation. And he is also great mind of today's times, and really great person of today's CFD all over the applications available, right? So great mind. We are so lucky we have him here. Okay. I think this was just a brief introduction. I think we can close the camera off. So let's close the camera off. Yeah. So for now, just our faces disappear for a while, and I will go ahead. So about the webinar. So the webinar is going to take up to 1 hour, depending on the number of your questions and reminders. There will be 3 parts in this webinar. In the first part, I will give a general introduction to Turbomachinery CFD. I'm going to point out the main Turbomachinery CFD features and benefits. In the second part, there will be a live demo, a live example, where Radek is going to show you how to simulate a centrifugal compressor in Turbomachinery CFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window below, or you can also send us an email to info@cfdsupport.com, and we will answer all your questions and reminders later in this webinar. Especially in the beginning, we are going to be quite general, but feel free to put your questions, and then we can go to the details, and we will really provide all the information. So about the CFD Support. So CFD Support is a private engineering company dealing with computational fluid dynamics, or mainly with computational fluid dynamics. We are located in Prague, Czech Republic, and we are used to deliver complete CFD engineering projects. We do project work on demand or all across the CFD field. We also do quite a lot of outsourcing work. Then we deliver extensive open form training and consultancy, as well as we are used to deliver open form support and custom development. And of course, our flagship product is Turbomachinery CFD, which is today's webinar about. Which brings me to the Turbomachinery CFD. Let me give a brief description what Turbomachinery CFD is. So Turbomachinery CFD is a unique software based on OpenFOAM. It was designed for CFD simulations of all rotating machinery such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, etc. Both radial and axial machines, both compressible and incompressible fluid flows. Turbomachinery CFD is complete CFD workflow that covers all the engineering steps from pre-processing over the simulation run to the very detailed post-processing of the results. So it's independent on any other software, and on the other hand, it's fully compatible with standard OpenFOAM version. So for this reason, Turbomachinery CFD is a comprehensive package, comprehensive CFD simulating package. Let me put just a quick review of its unique value proposal. We believe Turbomachinery CFD is unique at least for 4 reasons. Number one is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores, and that this property gives the investment in Turbomachinery CFD a permanent value. And also this means our clients can scale their CFD simulations in a really big way because everything is unlimited. Number two would be Turbomachinery CFD is fully automated, which means all the workflow from the initial data to the final results report, it can be run by a single command or a single click, and all the process is being done automatically. For this reason, Turbomachinery CFD is extremely effective. It's really extremely effective because it's really automated and the engineers can decide how deep knowledge they input in. But yeah, the automation makes it extremely effective. Number three would be we deliver fantastic technical support. We are proud of it. We keep custom approach to every customer, to every issue. We never leave behind any of our clients, and we are very flexible in it. We support our clients even in matters out of the turbomachinery field. For example, in numerical mathematics, physics, in CFD, IT, or even software engineering. And the last one would be the real tutorials are included. So TCFD user has no doubts about the best practice settings. So there are included the real machines that are already preset. So you can basically take one of those tutorials or preset machines, replace the geometry with your own, modify the settings, the boundary conditions, for example, and just run the simulation. So it's prepared, it's ready to use. Yeah, so there are many other benefits of using Turbomachinery CFD. I'm not going to go for all of them, but these 4 are, I would say, those are the major benefits or unique value or values. Okay, there are some important technical details. I will just briefly go over them. So Turbomachinery CFD is available both for Linux and Windows operating system. The workflow is very the same in Windows and in Linux. That's important. The Turbomachinery CFD workflow is fully set from a graphical interface. The graphical interface is ParaView. You can also work from a terminal, but most people prefer to work from the graphical interface. Of course, Turbomachinery CFD can be also run on clusters, clouds. It's ready for it. So for this reason, your CFD simulations can be scaled in a big way. But the decision is always up to you. Important is that 100% of the workflow is in the graphical interface. No command line anymore. Of course, you can use it. It's also there, but you can stay in graphical interface, which is a really important message for me right now. Turbomachinery CFD is transparent. So the trial version is available for free for a 1 month period of time. So anybody can try Turbomachinery CFD, and afterwards he or she can decide to go for it or not. The real tutorials are available of all important machines or machine types. That's important. Every single simulation has detailed report in HTML format, in web responsive HTML. So every simulation has a report which can be updated anytime. It can be stored, and it's very practical and extremely effective because you do not need ever to evaluate results manually. You just read the report all the time. The report is ready for you. You just evaluate. You evaluate in your head, right? But you always look at the results in the report. No special evaluation is needed. It's done. It's being done automatically, which is important again. The Turbomachinery CFD includes visual post-processing tool called TurboBlade Post, which is a special set of software plugins for ParaView. Workflow is fully automated, and it can be further scripted in Python if necessary. And it can be it can be connected with other softwares via this through this scripting. And perhaps this is my final point with this. Perhaps the most important information from today's webinar is all the information is available online. So take a look on our website, and you will learn everything. And you can also get back to us, and we will gladly answer if something would remain unclear. So that was the introduction of Turbomachinery CFD. Now it's coming time for the live example of Turbomachinery CFD. So today's example will be centrifugal compressor. So I will turn my attention to Radek. So Radek, are you ready for your part of the presentation?
Yeah, hello again. I'm ready. I'm ready. You can give me the presentation.
Perfect. So I will click give control. I will do the make another attendee presenter. I'm making you presenter right now. Okay, perfect. So it's yours.
So I hope you see my screen. Yeah, perfect. So hello again. I think that Luboš already said all important details and all important information about our software. So I will dive directly into the practical part, which is an example of the usage of our software. So now I am in the Windows system. So now I'm using the Windows version of our software, and I can directly start running a ParaView, which is a third-party software which is directly connected to OpenFOAM, and we have developed an interface directly into ParaView to manage all workflow, all standard process for setup CFD case. So I will simply click on it. So I will run ParaView. So now this is standard ParaView of this version 5.0.0. And to start working with our software, there is a simple source which is called tcfd source. So I will click on it, and now new set of how to say outlines, or a set of parameters which can be applied. So I will just undock this window to see everything. So basically, this tcfd source can be used for setting standard CFD case. So basically, there are many menus. In the general menu, you can load, save your actual setup, or you can load some preset setup. So I will do it because today's case is a centrifugal compressor. So I have already downloaded from our web pages. So I will go to my working directory. This is this webinar, and here's the radial compressor. So you can download it and use it. So I will load this radial compressor, which is preset setup for this case. So I will directly load it and click on apply. So when this configuration file is loaded, you will directly see here the geometry. So the input in this case is standard STL geometry, which is split into 4 parts. As you can see, the white one is the impeller part, then the red and the green part is the extension. It's from impeller to the volute, to the stator part, and in the blue one the volute is depicted. So this is the input of our software, and in these menus you can see, or you can change a lot of parameters which defines your simulation, which defines your geometry. So for example, in coordinates, standard coordinates of axis of rotation, in geometry there are some other parameters. If you are not sure which parameter or how can we use this parameter, you can just point by your cursor to this window, and the help will appear, so you can read directly what each parameter stands for. Then you can set standard physics, dynamic viscosity, reference pressure, fluid, air or water, and so on. Again, turbulence models, you can choose between k omega st k epsilon or without any turbulence model. In the speedline part, you define the simulations, the points, simulation points for your simulation. That basically it is the speed rotation, and for each speed rotation you can define as up to 10 points, 10 computed points with different boundary condition, with different pressure drops, with different flow rates, and so on and so on. The speed line can be changed using this bar, and yeah, for each speed line you can change amount of point to be computed, and these numbers are just maximum number of iteration to be computed for each point. As I said, each point is connected to different boundary conditions. So at the inlet you can choose between, for example, mass flow rate, volumetric flow rate, directed volumetric flow rate. If you want to change the direction which goes inside your domain, or total pressure, because this case is compressible, so you define for each point the inlet temperature, inlet total temperature in this case, and so on. For example, in boundary outlet, again you can define fixed pressure or outlet vent boundary condition, and again for each point you define the specific value. If we go further in the simulation, this is an important part. Our software provides both steady state and transient simulation, so you can compute in steady state or in transient, which is more computational demanding, of course. You can simply change the amount of processors, and here are some bounding parameters, so you can make your computation more robust if you specify this bounding values, but it is not necessary because they are set as default, or the default setup is really robust for any computation. You can choose between first and second order for numerical order. In the numerics and other advanced parameters to set up initial conditions, initial pressure, initial velocity. So you have to set some reasonable value from which the computation can start. And important part is the components part. Here you simply define your geometry. So our workflow is that each machine is composed of several components, which one component has, let's say the physical meaning. For example, one component is stators, second component could be impeller, third component could be just the volute part, and so on. So this geometry is split into several parts, and this number of components is defined here. For each component, you should define how to create the geometry. There is several options. This case works just with the definition using surface geometry in STL formats. So the computational mesh is automatically generated using standard OpenFOAM mesh solver, which is called SnappyX mesh. So in this case, you just say where to find the geometry. So in this STL directory, you can name your component as you need, as you want. Our software provides also simulation for periodic segments. So you can simulate just, for example, one blade of the impeller. So if the blade has 20 blades, so you will define here 20 periodic segments. And here in this list, it shows all input geometry in this directory, and you simply choose which one corresponds to your component. So this is the impeller part, this white part, and you just check which geometry to use. You will set the type, standard type blade, wall, or each part of the impeller, what is the inlet, what is the outlet, and so on. You can set the minimum and maximum level of refinement. For SnappyX mesh, you can define the boundary layer. If you need to use some turbulence model which needs boundary layer, or to decrease the Y+ parameter, for example. And for the communication between these interfaces, for example here for steady state case, to define communication between the rotation part and stationary part, there is this column which is called MXP. So if this number is non-zero, positive and non-zero, it means the mixing plane approach will be applied on this interface, and this number defines the number of mixing planes. And other parameters are to improve. This is some advanced parameters to improve the meshing process. So you can define, if you know the distance between, for example, trailing edge and the outlet from this component, you can define it here, and it increases the robustness of the meshing process. Standard background mesh size, it means the largest size in your computational mesh, and internal point, which defines the part of the geometry in which the computational mesh will be generated. During the creation process of the mesh, during the definition, you directly see here nice topology of your mesh, which is really interactive. For example, I can define, for example, next component. You can directly see here. I can anytime I can change the name and so on, and you directly see what is happening, how is your topology changing. So it's really interactive and easy to manage your mesh and the geometry setup. Well, and these are other menus for the meshing options. So these are advanced parameters for meshing options, how to define layers, and so on. So basically, there is any parameter which SnappyHex Mesh can use, and here in the post processing you can define, for example, if for which interfaces or which interfaces you would like to use for evaluation of efficiencies, pressure drops, and so on. So you can add, for example, just impellers, so inlet patches. You will use where is it? Yeah, here, rotor inflow, torque patches, for example, just rotor blades, and outlet patches, rotor outflow. Okay, and after the computation is done, or even during the computation, you will see efficiency just for impeller and other parameters just for the part you have defined here. The scripting part, here you can load a simple Python script. So if you need to use any boundary condition which is not defined directly here, or if you would like to use some or any different turbulence model, so you can define it using scripting language, using the scripting part and using the Python scripting. Okay, so if you are satisfied with your setup, so I have changed a lot of parameters, so I will load it again, the default one. So if you are satisfied, then you can click on the settings item in this pipeline browser, and then the TCFD manager is activated and you can apply on the settings menu. So using this TCFD source, you can set any parameters, you can set the mesh, and using this TCFD manager, you can manage the computational process. So basically, important part is directory name. So you can define your case name. So for example, for any simulation, for any I don't know, for any modification of your geometry, you can set up different directory name. So for me, my webinar case, for example, I will click on apply. After that, then other buttons will be activated. So first, I need to write this case. So it means this TCFD manager create the standard OpenFOAM case and its topology to run the case with your setup. And after that, the case is written. You can use this all run by one click button, let's say, run all, and it will run whole process of CFD workflow. It means at the beginning, it creates the mesh. After the mesh is created, the calculation is run. And here, when the calculation is running, you will see which point is computed, which speed line is computed currently, and overall information about the computation. There is also a guess how long does it take, and so on. You can anytime skip to next point. You can anytime abort the calculation and run it again, or run it from the last computed point. And what is really useful, anytime during computation, you can update the report and see the result or see the evolution of your computation. So now we can see that at this time the first component is meshing. So when the computation is done, or during the computation, I have prepared here, you can see these windows. So you can see just, for example, the mesh to check if your mesh is okay. it is simply done here. You can click here on show. So if I need to visualize just impeller part, which is, I guess, component 1, so I can click on show and then click on apply, and the impeller part will be visualized. So yeah, now here the impeller is. So you can check it, you can make slices, so you can analyze it as you want. And what is important, in the next window there is a complete CFD report, report for your computation. So this is the report at the end, but it can be generated anytime during the simulation. So we will slowly through this report. So if you are using more speed lines, so you can go to each speed line, and at the beginning you will see overall figures for the whole simulation. So it means you can see here 3 speed lines with several points which we have defined. So here's the efficiency for each speed line. Here we can see the plot of total pressure differences. You can see here the total pressure ratio for each speed line and for each point. And then the report continues with a lot of parameters for each speed line. So we are starting with speed line 1, which corresponds to the setup speed 160,000 RPMs. And here are all important information in one place. For example, average Y plus, how long does the computation takes, how many processor was used, and the compressibility mode or the used fluid type. So in the first section there is the efficiency for each computed point, and again the graph of the results, and also the graph or the figure of the convergence process. So you can see the evolution, if you can see if efficiency is converged, if there is no oscillation, and so on. The next part is the torque. So again, for each point you can clearly see the torque. You can see the figure again, and also the process of the iteration process. So you can see the values for every iteration during the computation. Next part is total pressure difference, again with the similar tables, similar lists, and similar figures. Total pressure ratio, total pressure per interfaces, so it means there is a value for each interface, so starting from the inlet, from the first interface between two components, and going to the end, to the outlet. So we can see the distribution of the pressure during your or through your domain, through your geometry, through your machine. Total temperature difference, again, and total temperature per interfaces. And last but not least, the velocity magnitude per interface. So you can see directly the magnitude of velocity for each interface, and circumferential and meridional angle for each interface. So you can see if the flow has a correct or expected direction, for example on impeller, and so on. And there are next part which corresponds to the speed line 2, which corresponds to the to the speed of rotation 150,000, and there are similar parameters to read. So you can save it as PDF, or if I go to this directory where this case was computed, so in here in the radial compressor computed, there is OF case 0, which is the default name for previous computation, and here you can see directory report steady state, and here is the HTML, and you can see the results anytime anytime after your simulation. Well, moreover, you can save this as PDF if you would like to print it or share somewhere, so it's up to you. So this option exists. Okay, so this was, let's say, the information about the results in the written form, but you can also visualize almost anything you need. So I can go here. I have prepared some visualization. So basically in ParaView, you can, okay, or I can show you how to start it. So in any case, there is a file with name case.foam, and just by clicking on it, you can open this case. You can choose, for example, the geometry you would like to visualize, for example, just rotor shroud, rotor blades. You can click on apply. Now this is the initial condition, because here we are at time 0, so it corresponds to the point. So if I would like to go to the point 4 with respect to my setup, and I can see the pressure distribution on shroud and impeller. So anytime you can, or anytime after the computation is performed, is done, so you can visualize what you want. So here are some examples. You can visualize just, for example, impeller with the streamlines. Here is just the slice with a total pressure distribution on your geometry. Then, for example, there is a nice visualization of one slice with the glyphs on it, so you can see the direction of the flow for at the chosen slice. Okay, next time can be again the impeller with 3D glyphs, so you can follow the streamlines. And so this was the standard utilities, but we have developed some advanced filters. So first one is meridional average, and the filter is defined here, meridional average, and it can be simply applied to this case foam, and it is basically just meridional average of the values along the impeller. So you can nicely see the pressure drop, the average pressure drop on a blade, for example. Other tools which we have developed is, for example, blade-to-blade view. This parameter is called turbo unwrap, so you can apply it again on your case. So first options is, for example, to visualize the radial slice it at 50%, because what basically do this filter, it unwrap the wheel into the hexagonal domain with the coordinates 1 times 1 times 2 pi, I guess, and you can nicely do the slice in which corresponds to some percentage between shroud and hub, and on these slice you can visualize what you want. For example, streamlines colored by the static pressure, or you can visualize just the blades and the pressure contours on these blades to see the pressure distribution on blades. So this is nice plugin which is called Turbo Unwrap. Well, so basically you can work in one ParaView. You can see the report, you can see the defined geometry, you can see setup parameters, and then if you open new render window or new ParaView, you can evaluate any part of your geometry. So I think this is really comprehensive, that you can do everything in one window using one viewer. You can directly see the process of simulation. So it is really nice. So I think I am at the end of my part. So I guess it is time to give the presentation back to Luboš. So Luboš, are you here?
Yes.
Perfect.
Yes, I am. So thank you, Radek. It was great. So thank you again for your remarkable life example. Thank you very much. So yeah.
Okay, so I can give you the presentation.
Okay.
This is here. Okay, so the presentation is yours again.
Okay, so it's back on me. So yeah. So that was the technical part, the example, and now I will quickly finish my presentation. So I'll go for it. Yeah, before I do that, I would like to kindly ask you to give your questions. Just take your chance. It's your time. We are here for you, so we feel ready to serve. So put your questions. It's still time, and yeah. So I'm gonna finish with how to get Turbomachinery CFD. So the demo version, the trial version is available. Anyone can try Turbomachinery CFD full version for 1 month and decide to take the action or not after that, after he makes sure everything is as expected, as good as expected, and works properly. So after that you can decide. So you have nothing to lose. Everything is clear and transparent. The paid version is always perpetual. So once you pay for Turbomachinery CFD, it's always perpetual. Our clients can keep Turbomachinery CFD forever. What's important, what is paid for with Turbomachinery CFD is the first delivery and technical support and maintenance, right? So, and the updates. So again, with Turbomachinery CFD, what's paid for is the first delivery and technical support and the maintenance. You can keep the software forever. You can use it without any limits for unlimited number of users, jobs, or cores. So that's a huge benefit comparing to what's available in the market. Yeah. So we believe Turbomachinery CFD is very affordable. We decided to fight hard for universities. So universities pay only 3,000 euros. And private organizations pay 12,000 euros. Yeah, so that's the pricing. I believe it's clear. So the software is always perpetual, but technical support and first delivery is paid. And those are the ratings. So if you have any questions, feel free to contact us, and we will answer all your questions. So which brings us to the latest, to the very or almost the second latest slide. Yeah, it's the Q&A session. So now it's time for your questions and our answers. So let me give a look what we have. So yeah. Okay, here it is. So we have a couple of questions. So first one. Karim is asking, can you describe what are the transient / steady state options in Turbomachinery CFD? Well, yes, we can. I would maybe, Radek, are you there?
Yeah.
May I ask you
Perfect,
to give the
Yeah, I can answer it. So I will take
yeah, please.
Presentation. Perfect. So I will go to our setup. So here in the settings, right? Yeah. Okay. So this was about the simulation, right? So you can choose, or you can, with respect to your simulation, with respect to your case, with respect to your problem, you can distinguish between steady state, and here is a steady state plus transient. It means if you would like to run transient case, so Anyway, you have to choose this steady state plus transient option. And it means that for transient, to speed up the computation and to make it more robust, the transient case is, how to say, it's pre-computed in the steady state mode. And the result of the steady state mode is used as the initial condition, as the initial condition for the transient simulation. So basically, for steady state and transient setup is always the same, but in addition, you just defined the time the time of computation, the real physical time of computation for each point. So again, you can define it using revolution per point. So it means the simulation will take 4 real rotation of your geometry, or you can just set it in the seconds. Yeah, so you have these two options, and the other setup is the same. Yeah, so this steady state / transient means that it performs transient simulation, but it is initialized by the steady state computation. So I hope the question was answered correctly.
Okay, thank you, Radek. So let's move to the next questions. And yeah, Marcus is asking, can I use my own turbulence model in Turbomachinery CFD? So what do you think, Radek?
Yes, sure you can. If your turbulence model is compiled in standard open form, then there's a way how to put it into our software using the scripting part, which is here. So we can help you with setting the script. So basically, just using the script to modify some parts in the football case, and which allows you to use your own turbulence model. So this it can be performed using the
Okay, thank you. And perhaps the last question is, Andrew is asking, what is the difference between standard OpenFOAM and Turbomachinery CFD? Maybe I would answer that. I would answer this. So I'll take the presentation back to me. Yeah. I think the best way how to answer this question is to going to my web browser. I'll go online to Turbomachinery CFD website, which is CFD support / Turbomachinery CFD, and yeah, it's the Turbomachinery CFD main website, I would say, and about in the middle. There you can see there is a table where you can see just the basic information, what's included in Turbomachinery CFD, comparing to standard OpenFOAM and comparing commercial software. So there you can see, for example, comparing now we are speaking about the differences between standard OpenFOAM and Turbomachinery CFD. So let's take a look what's different. Of course, it's a lot. It's 5 years of engineering work in a team. So Turbomachinery CFD was especially created for rotating machinery, which standard OpenFOAM is not ready to solve at all. So there are robust solvers which can take extreme fluid flows. There are new boundary conditions for turbomachinery, solvers for turbomachinery. There are real tutorials included. There are special plugins for pre-processing and for post-processing. Of course, all the workflow is automated. Turbomachinery CFD can be used both in Linux and Windows. There is a special reporting system. There's a graphical interface. Yeah, there's so many new things and differences which make Turbomachinery CFD available to be used on rotating machinery problems. OpenFOAM is just a set of tools which is not ready yet to simulate any real turbomachinery or any real industrial turbomachinery problems. That's it. Yeah. Turbomachinery is the extension of OpenFOAM, specialized to turbomachinery. So that was the difference. And yeah, I will take a look. Yeah, we haven't any questions anymore, so I think this is it for today. Maybe we will just conclude. So let's put the camera off, switch it off. So yeah, it's us again. We would like to thank you for your attention. Thank all the participants. There were many of you today. We are so lucky you and satisfied. We are so fine. We have so many followers. Thank you for your attention. We think Turbomachinery CFD is great software with a huge value for the customers. It brings a huge value comparing what's available in the market. So Radek, is there something you would notify?
Well, thanks you for watching, and yeah, we are looking forward to cooperate with you, to help you with your problems, and so do not hesitate to contact us. And yeah.
So this seems to be it. Thank you for your attention, and yeah, see you someday somewhere, and we will be looking forward. You will work with us. So bye bye. Yeah, thank you for your time.